So in this example, when we look at the system of equations, we notice that we have 2 variables and 3 equations. So this represents an overdetermined system. We have more equations than variables. This fits this slide to where we have the number of equations that's greater than or equal to the number of variables. We could get an answer that has no solution, exactly one solution, or infinitely many solutions. But our solution, if we get one, is going to be an ordered pair. We only have an X and a Y, all right? So we'll have an ordered pair. We can proceed with the normal steps as solving a matrix, putting it in reduced row reduced form. We'll begin by writing this as the matrix. Notice in the coefficient side, we only have 2 columns, but we have 3 rows. And when we begin to solve this, we already have the 1 in the first position, so we want everything else to be zeros. And we do this by taking row 2 and adding the additive inverse times row 1, and row 3 minus 4 times row 1. Row 2 minus row 1. That's 0, -4, and -4. And then row 3 minus 4 times row 1. -4 times row 1, that is -4 times -8 and -16. That gives us 0, -5, and -4. All right, so now first column is done. Now we want the second entry in the second column to be 1. And we can multiply by the multiplicative inverse, -1/4. Everything else remains the same. That's going to be 0, 1, 1. And now we want everything else in that second column to be zeros. So that 2 and the -5 should become zeros. And we can do that by taking row 1 and adding the additive inverse. And the same thing with the row 3. Add the additive inverse. So row 1 minus 2 times row 2. -2 times row 2 is 0, -2, -2, which is 1, 0, 2. And row 3 plus 5 times row 2. 5 times row 2 is 0, 5, 5. So we have 1, 0, 2, 0, 1, 1, and 0, 0, 1. And so since this last row, the coefficient side are all zeros, but the right-hand side is not 0, right? This is a false statement since 0 does not equal 1. So this would be a case where we have no solution. So our three lines do not intersect at a single point. Now, what would it look like if we did have a unique solution or infinitely many solutions? If we have a unique solution, then the row-reduced echelon form, the row-reduced form, would be something of the effect to where the last row are all zeros. Okay, because we have that, we know that x is equal to 2, y is equal to 1, right? And that third row is not needed. If we have infinitely many solutions, then we would have 2 0 rows. Right, that may be something like 1, 1, 2, and then the next 2 rows are all zeros. That would be an infinitely many solution case. And in the infinitely many solutions, all three equations have the same graph, have the same line. And for the unique solution, we have 3 distinct lines, and they all 3 intersect at that point, such as in this case, 2, 1. And now for our last example, we have another system of equations. Let's count the number of variables and the number of equations. We have 1, 2, 3, 4 variables with only 1, 2, 3 equations. This is an underdetermined system. An underdetermined system is when there are fewer equations than variables, such as our case. We have 4 variables, only 3 equations. Then in that case, the system either has no solution or infinitely many solutions. Okay, so it's impossible to get a unique solution here. So let's see how this plays out. Writing this in matrix form. 1, 2, -3, 1, -2, 3, -1, -2, -4, 1, and 2, 3, -5, 1, -3. Okay, we'll begin by working with the first column. First entry should be 1. It is. So the next entries should be 0. Okay, so we have row 3 minus 3 times row 1, and that should have been row 2. Row 3 minus 2 times row 1. I'll change that guy to an R2. Row 2 minus 3 times row 1. Okay, so row 2 minus 3 times row 1. -3 times row 1 is -3, -6, 9, -3, and 6. That is 0, -7, 7, -7, 7. And row 3 minus 2 times row 1. -2 times row 1 is -2, -4, 6, -2, and 4. That gives us 0, -1, 1, -1, and 1. All right, so now writing the updated matrix, we have 0, -7, 7, -7, 7. 0, -1, 1, -1, 1. You may notice that row 2 and row 3 are multiples of each other, okay? And the same multiple for the right-hand side. So we should be able to get infinitely many solutions from here, but let's keep going so that we can see that. So we want this to be a 1. We can do that by multiplying by the multiplicative inverse, negative 1/7 times row 2. So that would be 0, 1, negative 1, 1, negative 1. And now I want everything else in column 2 to become zeros. Which is accomplished by adding row 1 to negative 2 times row 2 and row 3 plus 1 times row 2. Okay, so negative 2 times row 2 is 0, negative 2, 2, negative 2, 2. So that's 1, 0, negative 1, negative 1, 0. And row 3 plus row 2. That gives us all zeros. All right, so let's see. So now we have 1, 0, negative 1, negative 1, 1 for the first row. Then all zeros for row 3. All right, so column 2 is done. So next we would ordinarily go to column 3 and make the third entry in column 3 to be 1, but it's a 0. So that cannot be done without messing up what we've done in the previous columns. So this is considered to be row reduced form. All right, so we're looking at that row of zeros. If the right-hand side is also 0, that means we have infinitely many solutions. If the right-hand side were something other than 0, that's when we would have no solution for this case. Okay, but we have infinitely many solutions here. So we want to be able to write our answer as that ordered quadruplet. All right, so to interpret this, we have x plus 0y minus z minus w is equal to 1, and 0x plus 1y minus z plus w is equal to negative 1. Okay, and that's all we have. So we can write x and y in terms of z and w. We would consider z and w to be our independent variables. X and y are dependent. They depend on what x and y, z and w is. But this z and w are free variables. They can be anything. So we can write our solution as our x is z plus w plus 1. Y is z minus w. Z can be anything. W can be anything. So we have infinitely many solutions, with this being the general form for those infinitely many solutions.